All right, so this morning we're going to talk a little bit more about conservation of energy, and we're really going to focus on three main forms of energy. We're going to focus on dealing with kinetic energy, we're going to focus on gravitational potential energy, and we're going to focus on elastic potential energy. And all three of these sort of fall into a category called mechanical energy. So let's write those up there. We have kinetic energy, and I tend to use the symbol just KE. All right, you might see E sub K in a textbook or something like that, or online, same thing. But KE, kinetic energy, is the energy an object has due to its motion or its movement. And the formula for that is 1/2 mv squared, right? 1/2 the mass times the velocity squared. And that's your formula for kinetic energy. Now, gravitational potential energy, I'll write that as GPE. You'll also see in some textbooks, you'll see like a U sub G, U being potential, G being due to gravity. Gravitational potential energy is equal to the mass times the acceleration due to gravity times the height, okay? And the third is elastic potential energy. That's energy that you store in an object when you stretch it or compress it. And elastic potential energy is EPE. You'll also see that in textbooks as U sub S, S for spring, and U for potential. But the formula for elastic potential energy is 1/2 kx squared. And those are kind of some weird variables. We'll talk about those. So real quick to recap, kinetic energy is energy due to motion. So anytime we're moving, we have kinetic energy. Gravitational potential is due to height. Anytime we're above a frame of reference, all right, above a surface, above an object, whatever, potential to fall, do damage, so we have gravitational potential energy. And elastic potential energy is due to deformity. So anytime we change the shape of an object, that would, when released, naturally return back to its normal shape. Usually that means there's elastic potential energy in that object at that point in time, okay? Those are our three formulas. We know M is mass, V is velocity, G is gravitational acceleration, H is the height. These two variables are kind of different. X represents the distance that we've compressed or stretched something. So if I take a rubber band that's normally 6 centimeters long, and then I stretch it to 15, well, the X is the 15 minus the 6, the change in length of our substance. That's our X. And then K is what's called a spring constant. So similar to mu, in the sense that mu kind of describes the material. K also describes the material, describes what we're stretching. So if I have a really, really flexible object that's pretty easy to stretch or compress, then we say that object has a really low spring constant, low K value. If you're looking at something that's really hard to stretch, like maybe like a diving board or like one of your garage door springs, or I mean, really even a big piece of metal has a little bit of flex or bend to it, but it's really hard to stretch or bend, then that tends to have a high K value. So your spring constant just tells you about the stiffness. If it's really stiff, it's going to have a high K. If it's not very stiff, it's going to have a low K value. It tells you about those things. So these are our three formulas. And when we talk about energy being conserved, we basically say that the initial energy, that's what we start with, and that could be a combination or one of those forms of energy. The energy we start with is going to equal the energy that we end with. All right? In other words, in the process of starting with a certain form of energy, I don't ever lose that energy. It just changes from one of these forms to another. So the total amount, the quantity I start with, has to equal the quantity I end with. And we're going back to our poker illustration. We have no rake. All right, no rake at all. Our energy is conserved throughout. Okay, and that's what we're going to be doing with these problems. We're going to be doing kind of scenarios where we really have no energy loss, energy dissipation here. We just have this constant transfer of energy from one of these forms to another. And what that might look like is, okay, I drop an object from the top of a building, and I want to know how fast it's going when it gets to the bottom. Now, we could use classic motion equations and solve for that, or we could set up a conservation of energy type problem. And let's do that real quick. Let's say we drop an object off a building that is 100 meters tall, for number's sake. So we have this building here. We're 100 meters in the air. We drop an object, and we want to know when the object gets here, what's our velocity? What's our velocity? And so one way to look at this, again, we can use motion equations. Initial velocity is 0. Delta y is negative 100. We know acceleration due to gravity is negative 9.81. Or I could look at this and say, wait a minute, I know that the energy I have up here, which is gravitational potential energy, has to all be converted to the energy down here, which has to be kinetic energy. Does that make sense? So we'll set that up mathematically, and we'll say, all right, well, my initial energy, my GPE, has to equal my KE, or if I write that out in formula form, we have M times G times H is equal to 1/2 mv squared. Now, one thing that happens that's really nice in this equation is I have an m in each term, so my m cancels out, and now it's just a matter of plugging in. We have 9.81 times 100 is equal to 1/2 v squared, right? So to get rid of the 1/2, we multiply both sides by 2. And then to solve for v, we're going to end up taking the square root. So we have v is equal to the square root of 2 times 9.81 times 100. And let's look. We end up with the velocity of 44.3 meters per second. Okay? That's just an example of what you can do using conservation of energy. So I've given you some problems involving different forms of energy conversion. Sometimes you just have 2 forms of energy you're dealing with. Sometimes you're dealing with more. Sometimes you're dealing with multiple of one converting to some of the other. So the first thing you'll have to do in these problems is identify and say, okay, what types of energy am I dealing with at the start? And then what types of energy am I dealing with at the end? And kind of split that up. One of the classic problems that you might deal with is a roller coaster type problem. So we have this roller coaster, we go over this first hill, and we want to know, hey, how fast am I going at the bottom, or how fast am I going through the first loop, right? So we have this roller coaster here, and we're going down. Here's our loop of some sorts. Here's our roller coaster, and it's going this way. Maybe at the top of the hill, it's moving at like 3 meters per second, right? So we obviously up here, because we're moving, we're going to have some kinetic energy, right? And we're also going to be up in the air, so we're going to have some gravitational potential energy. So we're going to have a split of those things. Down at the bottom here, we're just going to have kinetic energy. And then as I go through the loop, I'm also going to have like a mix of kinetic and gravitational potential energy. And that mix is going to depend a lot on how high I am. If I'm at the top of the loop, it's going to be more GPE and less kinetic, and vice versa. And so we can kind of mathematically go back and forth. As soon as I know the total amount of energy in any of these spots, I know that has to equal the total amount of energy in any of these other spots. And that kind of helps me work through these problems. So I think that's it for this. I'll have some activities that I'm going to put on Schoology for you to help you with energy conservation. Just get the idea down, and then from there, we can work at doing some of these problems for homework. Thanks.